Welcome to Unit 4 on Genetic Algorithms. In this unit, we will discuss the survival of the fittest or the selection process. That is, how fitter individuals survive while weak individuals fade. For selecting fitter chromosomes and allowing these to reproduce new offsprings, we use an algorithm called Roulette wheel selection or importance resampling. Before going into the details of this algorithm, let's briefly recap what we have already discussed in the last units. We are understanding the genetic algorithm process using a simple problem. We have a linear function f of x, which is defined as x1 plus 2 times x2 plus 3 times x3 plus 4 times x4 is equal to 30. And our job is to find x1, x2, x3 and x4, which solves this linear equality and f of x. So we started with ensuring that our potential solution or chromosome is 4-dimensional. R has 4 genes. And this is in conformity to the 4 unknown variables, which are x1, x2, x3 and x4. Then we set the population size to 6 potential solutions or chromosomes. Now these 6 chromosomes are randomly initialized in the starting. Some of these may be good and some of these may be bad. In Darwin's language, we can say some of the chromosomes are the potential solutions are fit and some are unfit, or some are less fit and some are more fit. So we have a fitness function which is written here. Then based on fitness, we obtained probability. And chromosome 4 has the highest fitness probability in the current setting, followed by chromosome 6 and chromosome 2. Now, how the strong potential solutions will carry forward to the next generation? That's the question. The algorithm used for natural selection is importance resampling or roulette wheel selection. And there are also other methods in the literature. So the roulette wheel selection will be discussed here, and it depends on the cumulative distribution function. So first we need to define CDF and how to compute it. The CDF or cumulative distribution function is used for evaluating the accumulated probability and is defined as shown here. Here the capital X is the random variable while small x is a point of interest in the probability domain. So here I want to emphasize that in some other courses you may have transformed some function from time domain to frequency domain using Fourier transforms, etc., and some other domains. So when we talk about the CDF and the PDF, we are mainly in the probability domain. Okay, so the CDF of a random variable x, capital X, evaluated at point of interest, small x, is the probability that p of x is less than or equal to small x. So a random variable stores probability which cannot be greater than 1 and smaller than 0. As earlier discussed, that CDF is used for evaluating accumulated probability. For CDF, we need PDF or PMF. PDF is the probability density function in the continuous domain and PMF is the probability mass function in the discrete domain. Now, basically the PDF or the PMF, it shows the shape of the distribution. It describes the shape of the distribution as shown here. Here we have 12 events and we can observe that event 3 and 4 has higher probability compared to others. As said on the last slide, PDF describes the shape of the distribution function and here it is bill shaped like Gaussian like. Now the simpler part, as we discussed earlier, CDF is used for evaluating the accumulated probability. So let's compute the accumulated probability. If we add the first two events probability, we get 0.02 plus 0.07, which is 0.09, which can be marked in the red color here. If we add even 2 probability to the last accumulated probability, then 0.09 plus 0.15 is 0.24, marked in the black color here. The accumulated probabilities can be computed using sum scan, which is running sum, and write the probability of each event, sum the first two probability to 0.09, then take this sum and add to 0.15 to get 0.24, and so on, and these probabilities sum to 1.0. If we see the CDF plot, some probability intervals plotted on the y-axis are small while some others are long. Interestingly, we can see that intervals at event 3 and 4 are longer and their probabilities are also bigger than others. This means that if the fitness probability of a chromosome or potential solution is high or low, then in the CDF representation for the population also reflects that accordingly. If we generate a random number in the range of 0 to 1, where it can lie, it can lie anywhere in the 0 to 1 range. But on the average, for longer range or intervals, the chances are high. Again, it means that if the fitness probability of a chromosome or potential solution is high or low, then the chances of carrying it forward, the chances of its survival are high. This is the main philosophy behind the roulette wheel selection. Now let's see some pseudocode for this purpose. First, in the literature, you can find different implementation of roulette wheel selection. One example is this paper, an adaptive and memory-assisted local crossover and genetic algorithm. Scrolling it down, table 3 outlines one way of roulette wheel selection. The roulette wheel selection is inspired from the size of sectors of interest on the wheel. The larger the size, the greater the chance of having the ball in the concerned pocket. Okay, let's see some pseudocode. Reproduce the fitness probability computed in the last unit. Then we can compute the CDF from this, which is required for the roulette wheel selection. Now we need a random number in the range of 0 to 1. We call it rand toss, rtoss. Now we can use any programming language such as C++ or MATLAB to generate a random number in the range of 0 to 1. In MATLAB, the rand function generates a number, a double number in the range of 0 to 1 from a uniform distribution. But in C++, rand returns an integer which is in the range of 0 to rand max. So we need to scale it by dividing by rand max, and we may also need to do typecasting in order to avoid division of integer by integer, which results in an integer. Okay, so whatever the language is, rtoss will be a number in the range of 0 to 1. Then we initialize variable I from 0, and now the question is, we also have rtoss, which is randomly generated in the range of 0 to 1. So where can rtoss lie? As the CDF is a non-decreasing function, so we can say while rtoss is greater than CDF of I, and then increment I and end. And whenever we exit from this loop, I is the selected individual. For example, if rtoss is 0.3, then 0.3 is greater than 0.12. So it's true, and I is incremented to 1. 0.3 is also greater than 0.27, so I is incremented to 2. And 0.3 is greater than 0.41, that's false. So I still remains 2. So we exit the loop, and 0.1408 is selected. Similarly, if rtoss is 0.4 or 0.5, then this individual is selected. To summarize, on the average, longer intervals on the CDF are individuals with higher fitness probability are more likely to be selected and carried to the next generation for reproduction. So in the next unit, we will discuss reproduction, and related topic are crossover rate, and mutation rate. So see you in the next unit, and for now, if you have any question, you can ask in the comments. Thank you.